This is the first lab of Physics 1. It is about a constant velocity motion. The experiment will compare the position as function of time in the two cases of experimental measured position and model predicted position. The model we will use is based on the Newton's second law. This slide summarizes the Newton's second law. The Newton's second law says that the final velocity is equal to the initial velocity plus the total forces acting on the object divided by its mass times delta t, where delta t is the time interval. Assuming that v is constant, we must have f net equals 0, so that the equation becomes vf equal vi. Let's call that constant velocity as v. In the same way, we can have that the final position of the object is equal to the initial position plus the constant velocity v times delta t, where delta t is the time interval. The experiment is about a bike and its biker. The x-axis is positive to the right. I used the tracker to get all the information about the x position as function of the time. This is the experiment setup. You can pause the video so you can read all the detailed information. In any case, the most important parameter is the initial velocity. The initial velocity can be calculated using the first recorded data or the last recorded data. Using the last recorded data, we will have an average velocity. Why the initial velocity is important? It is important because we are using a recursive formula in our computer model, so that a small error in the initial velocity can bring to a total wrong last position. The problem is that to be highly accurate in the evaluation of the initial velocity is not easy because of at least three causes. First of all, the real speed of the object is not really constant. Secondly, the end selection of the marker position on the tracker is not always perfect. And third, the sampling rate of 60 frames per second that I used with my camera might better recording the errors coming from cause 1 and cause 2. Therefore, I decided to do a double analysis using two different first initial velocity as discussed previously. This is the result of the experiment using Vi equal V1. The dotted line is the experiment position. The continuous line is the model position. We can see that at the end of the experiment we have big discrepancies due to the initial velocity. This is the result using the initial velocity equal the average velocity. We can see that the discrepancies at the end of the experiment disappeared. There are still few discrepancies in the middle of the experiment. Those discrepancies should come from the three causes discussed in the previous pages, and they should not come from the initial velocity value. This is the result using a flipped x-axis. To do that, I changed the sign of the velocity from negative to positive. Now we can say that the position is increasing in the position direction. Sorry, the position is increasing in the positive x direction. This is the case with f net not equal to 0. I've added a force in the x positive direction that is against the motion. I've chosen a force of 775 newtons, so that using the mass of 79 kilos, I have an acceleration of exactly 9.81 meters per second square. Since the force is positive, also the acceleration is positive. You can pause the video so you can read here the description of the motion. The position is a quadratic curve that comes from the integral of the Newton's second law. We can see that after about 0.5 seconds, the velocity changes its sign from negative to positive, and also that after 0.9 seconds, the position will start becoming positive. Here is the Python code where I changed the fnet vector value. Running the model, we can see how the object is moving. It starts in the negative direction and then moves in the positive direction following a quadratic curve. This is the fnet analysis. In order to maintain a constant velocity, the fnet must be 0. That means that the total forces acting on the object must be 0. There are 5 main forces in this experiment. You can pause the video so you can read all the details. In the end, we can say that in order to have fnet equals 0, we must have this equation about the horizontal forces and this equation about the vertical forces. In conclusion, we can say that the friction force with the ground must be at least great enough to equilibrate the driving force and the viscous friction force. In other words, we can say that thanks to the friction force with the ground, that here has been indicated with the vector F4, we can say that thanks to that the bike moves ahead. This drawing is to show how the viscous friction force F5 can be seen as a sum of infinity little forces acting on the object. Thank you.